All right, so we'll talk about machine learning. So last week, did a machine learning lecture for a regression problem, predicting the weather, the temperature of of one day in advance. So that's an example of a regression problem. Can anyone tell me the two major classifications of machine learning problems?
I know regression is one. I have the other one tip my tongue. I cannot remember.
Is the other one grouping?
Uh, Basically, yeah. So you can there's clustering, which is like grouping, and there's also classification, which is also kind of like grouping. So a classification problem is one where you have like a limited set of known possible outputs. Um, for example, is this email spam or is this not spam? So it can only be one of two things. Um, that's an example of a classification problem. A regression problem is usually something like I want to predict it, the output is usually something like a float. So I want to predict the cost of something at some point in the future given these conditions. All right, so why would you ever use machine learning for anything?
uh you want to build a program that gives you like an answer based on several conditional factors, maybe.
Okay, yeah. Yeah, several conditional factors. So, the example from last week. So if I wanted to predict or let's take spam, whether or not an email is spam. I mean, could you write a regular program to detect if an email was spam or not?
Probably.
Yeah, so if you wrote a function that did that, what would it look like? What would the function signature be?
You'd probably be using some kind of regex to like pick out keywords regarding spam, maybe.
Okay, so that would be the internals. What about so when I say function signature, does anyone know what that means?
Not off the top of my head.
It basically means what does it take as input and what does it return as output. So a function signature. So what would a spam detector function signature look like?
Maybe taking like the address as an input and then return a Boolean as an output.
Okay, so you could take in an email address. So that would tell you like if let's say a given email address was known to send a bunch of spam. So that would definitely be one way of filtering out spam.
You could pass in a list of emails and maybe get a return of good emails that are not spam, and the bad emails could just be deleted.
Yeah, you could do something like that. So if the function is basically like someone sends me an email and I want to know is this spam or not, I think the there are a few options. I think maybe the simplest thing would be the function takes the text of the email as an input and it returns, let's say, a Boolean. Is this spam or is it not spam? So the function signature would be, string to Boolean. So it takes the string as input and it returns a Boolean. Now the internals of the function. So how would you do that? So Tyler, you mentioned you could use some regex.
That'd be my first place I would start. Yeah.
Yeah.
I don't
So
know how easy that'd be, but
yeah, could you give me an example?
um, so I'd have to look at a lot of spam emails, I guess, and just see if there's any like keywords that stick out to me that kind of like, oh, that looks like, yeah, We could look for that. I don't know. That'd be the hard part, is I'd have to find, like, go look at emails myself and get a good idea of what I'm looking for, and then see if I can find that in multiple span, see if I find any correlations. So I feel like it'd be a lot of hand to work from me first before I can set it up.
Yeah, that's a really good point. So you'd kind of want to become like a domain expert, right? So you'd want to become an expert. You have to do some research maybe to figure out your own research. So you read through a bunch of emails and then say, does this look like spam? If it does, then are there certain patterns or keywords or anything like that? Yeah, so you could definitely do that. You come with a list of keywords. You might even do more complicated things, like if this word appears here and this other word appears later, then I know it's spam. Or if certain character combinations, the the
If it finds
problem-
Nigerian and Prince, we know that one's spam.
Yeah.
If it says chase.mail.com, you're probably about to be fish.
Yeah. Yeah, so we can come up with all kinds of, right? Like if there are 3 exclamation marks in the title, is that probably spam or not? And like all of these things, like there's a million things you could think of, right? There's just so many, and it's never ending, and there's not really a clear endpoint. And all of this is kind of like probabilistic, right? It's very fuzzy. Like, if my girlfriend sends me an email with 3 exclamation marks, is that should I just have a default filter, or should it be that in combination with some other things, or blah blah blah? So
Girlfriend could have been spoofed too,
yeah, exactly.
which case is probably malware, not spams. So I guess you're just looking at spam, not everything else, or
Yeah, so in this case, let's say we just limit the problem to, like, is this an email that I want to filter out? But yeah, I mean, so the issue is, like, if you actually think about, okay, I'm actually going to write a function line by line and do this, it starts getting very, very messy, and it's really not clear when it's done. And you could imagine writing a function, it's just going to grow. It's just going to be a bunch of if statements or regex checks or whatever. It's just going to grow and grow and grow and grow. It's going to end up being thousands of lines long, and then testing it and maintaining it and changing it is going to be a pain. So that's the kind of problem that you would want to offload to the machine learning model, because machine learning models are very good at taking lots and lots of variable fuzzy stuff and giving you an answer. So the downside of that is that you basically, it's a black box, right? So someone else has written it, right? This a model's been trained, you've trained it, but you really don't know how it works internally, and you're kind of just hoping for it to be mostly right most of the time. And then so yeah, so the kind of problem that you might want to reach for a machine learning solution is that kind of thing, where if you find yourself, if I want to add 2 numbers together, right, it's pretty clear, that there are a few different ways to do that, but it's pretty clear, I know when it's done, and there's a limited domain, and there's a way to get a correct answer. You could potentially write a machine learning algorithm that would add 2 numbers together without actually adding them together. You'd feed it a bunch of example inputs of, like, 3 and 5 is 7 and blah blah blah, and it I might actually try playing around with that this afternoon. But yeah, so addition is a problem that you could definitely solve with traditional programming practices. You could potentially solve it, although it would be very inefficient and kind of silly to try and solve a problem like that with machine learning. All right, so here's an example of a problem that humans are very, very good at solving. And we do it without really having to think very hard. So for example, you can look at this and know that these are the digits, 0 through 9. And this other list, even though this list is not exactly like this, and maybe you haven't seen a 9 that was exactly this shape and size before, but you can pull out whatever common information and you can make a judgment. You know that this is a 9, and you're not concerned about all of the little details. Computers obviously don't do that, right? Computers are very, very literal. So if you wanted to write a function that identified numbers based on an image, it would be very, very hard to do, right? Because one, you have to figure out what is the input going to be. You can't just give something an image and then blah blah blah, because it can't look at it. It can't use implicit knowledge and whatever complex machinery humans have. So you have to think about, how can I represent a number? How can I represent like an image of a number to a computer program? And there's a few different ways you could do it. One is you can divide up the problem like this and make it a grid. So you can take a grid and say, like, here's a square or something like that. So this is like a pixel or something like that. And you could say, is it black or white? Is it filled in or not? And then the next one, you could do the same thing. So you could represent this image as a matrix, or even like a database table or something like that. So you could do zeros for black and 1 for white, or the opposite, doesn't really matter. But you can take an image and then you can process it and translate it into something that a computer program can understand. And computer programs can understand matrices of numbers. What about something like this? So what if I told you that this was a letter? What might you guess that the letter is?
Should be A.
Okay, so why do you think it's an A?
Because it's alphabet 1 through 26, and the first one's 1. So just saying it's true, I guess.
Okay, yeah, I think that's so. So this is arbitrary. I could just be tricky and say no, it's actually it's actually Z because it's reversed or something. But as long as you're consistent, then yeah, this is one way to represent A. And so what would B be?
Second one would be 1.
Hmm.
The first one would be 0.
Yeah. So in this system, in this translation of the ASCII alphabet, it would be A would be 1 0 0 0 0, and B would be 0 1 0 0 0 0. So this is a way of representing a non-number thing as a list of numbers. So this is called one-hot encoding. So if you have a set of something and you want to indicate that something, something's a member of that set, it's this particular value within that set, then one-hot encoding is one way of doing that. This is often used to represent text, and it's not restricted to just letters, right? You could also use this for entire words, for example. So you could represent the entire English dictionary as an array of a bunch of zeros, and then your word is just going to be a 1. So the first word in the dictionary would be 1 0 0 0 blah 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 blah, right? That might not be the most efficient way, but you could definitely do that. Okay, So if we think about this problem of identifying a digit, this OCR problem, if we solve, okay, we have an image, now we're going to translate this into a matrix. So we have this. So we solved the first problem. Now we have to write the internals, right? We have to write the internals of this function that's going to figure this out for us. And you could imagine doing this, and it's just like, how would you do that? Well, you have to be very, very literal, right? You can't just say, well, you'll figure it out. It kind of looks like a 1 here. You have to say exactly what it needs to do. So if you get a matrix and it looks exactly like this, then we know it's a 1. But ones don't have to be exactly like this. They could be, maybe it's a little bit longer here, or it leans the other way, or whatever. So you have to go through, and this is a very limited problem domain, right? This is a 5x5 matrix. There's only so many possibilities. So you could hand code every single possibility and make a decision about what any given value is. But it's incredibly tedious, and it's a maintenance nightmare, and it's just not a principled way of solving this kind of problem. So when you have a situation like that, machine learning is the way to go. So when you're training a model, here's an example of training data. And training data for a supervised learning. So what's the difference between supervised learning and unsupervised learning?
You give it a model in supervised learning, right? You don't with unsupervised. You give it maybe an algorithm or something.
What do you mean by model?
Well, this training data is a model. I would say, because you're telling it that, these are the parameters, I guess, within which the number 1 kind of falls.
Yeah, okay, good. So in a supervised learning problem, we're giving the model, we're going to train the model with the input and the correct answer. So a supervised machine learning is, I have a bunch of data and I know what the answer is. In this case, here's this matrix representation of an image, and here's the correct value. So I can feed a whole bunch of this to the model, and the model can learn patterns, right? I give it a whole bunch of input and it knows the answer, so it can, it can kind of create its own internal structure that's based on the training data. In unsupervised learning, you don't have this. You don't have the correct, output. You basically just give it training data, and then so we're not going to talk about that. That's slightly more advanced. Okay, so if we're talking about a supervised model, then we need to take whatever input we have, let's say a bunch of images, like, I don't know, SVG images or PNG images or whatever. We take those images and we process them, and we turn them into, let's say, a matrix. And if we also have labels for those images, then we can use those and we put those together. So we start with raw data, images and labels, and we end up with basically arrays of numbers, because that's what machine learning models understand. They understand arrays of numbers. And once we do this, we can supply all of these pairs of, an observation, which is like this, and then a value, and the model can learn to associate those. So that's that's the basic outlay. So I know we talked about this last week, but last week was a little we kind of skipped the very beginning part. Any questions or notes about that?
Yeah, I try to think of it, and correct me if I'm wrong, like it when you train it, it creates a 3D array, which is I think of it as like stacking that matrix on top of the other, and then it just finds the best pattern.
I'm not sure. That's an interesting way of thinking about it. I'm not actually sure how things end up working internally. There are I think the example we'll see, you can actually get a visual representation of how the model looks internally, but most of the time it's you can't really know what the model is doing on a detailed level.
Is that kind of why this might be a little bit off topic, but I know like I like listen to a lot of podcasts and they talk about like the LLMs and all that, and I've heard like some scientists kind of really say like we truly don't understand how it works. We kind of know like like some basics and fundamentals, but how it truly works we don't understand. We just know that it does this, and we kind of keep doing it in a way. So I mean I don't know. It just kind of reminded me of that when you said you might not know exactly how it looks like under.
Yeah, there's like there's one of the first papers. Let me see if I can find it. Yeah. No. The unreasonable. What is it called? This. Yeah. So this is kind of a well-known blog post. And I think this is about image. I thought this was about text. Yeah. So if you want to check out this, it might be interesting as background, but basically you have this situation which seems crazy, it seems unreasonable, which is that you can generate text only looking at the individual character. So you can train a text generation model not looking at like grammar or words or like making semantic connections, just the letter. So I have a letter and then I have another letter and then I have another letter and then another letter. You can train very effective text generation models just using that. So it seems crazy, right? I mean, that's obviously not how humans construct language, right? We don't like take a character and then do some logical inference to arrive at the next character and then the next one and so on, right? But it works very well. And so yeah, like how does that work? Why does that work? I don't know. I mean, even in the like digital humanities, for example, if you want to identify authors, so there are you could use very sophisticated, even like subjective metrics for determining like, okay, was this play actually written by Shakespeare or somebody else? Was this poem written by Byron or somebody else? One way of doing that is to just like count the number of times the appears as a ratio to other words, right? So it seems it's incredibly stupid, right? On one level, it's very, very stupid. So I have this very sophisticated literary text, and now I'm analyzing it, and I'm just counting thes. So, okay, there's 10,000 words, and 1,000 of them are thes. But it turns out that stuff like that actually is fairly effective at identifying authors, right? So people have signatures, and no author, Shakespeare, I'm certain, was not thinking about like the ratio of the to everything else, right? So you can kind of model certain things using these unreasonable metrics. sorry, that was a little bit of a tangent, but. All right, cool. So I'm gonna walk through a couple examples real quick. So this one I have deployed and we can play around with it. So this is slightly more complex. And then this is a very simple kind of contrived example. So we'll do this one first. And I think I have this loaded up. So the yeah, let me grab this. So the idea here is that we like run a restaurant or something, right? So we run a restaurant, we have a thermostat, and we set the thermostat to a certain temperature every day. And we also have, customers will complain about different things. So we have these two streams of data. One is a temperature reading from the thermostat, and the other is, customer complaints. And our goal as the restaurant manager or whatever is to minimize complaints about the temperature. So we want to set the thermostat to the ideal temperature or temperature range that's going to result in the fewest complaints. And in this system, we're kind of eliding over how you would actually gather all of that data and process it, but that would be a real problem, right? So if you had people complaining through emails or through cards or whatever, you'd have to take all that data and put it in maybe a spreadsheet or something like that, and then process it later. But to keep this contrived example simple, we're going to say that we have all this data already, and that there are only 3 categories, right? So I have a temperature, which is a number, say like 72, and then I have some customer output. They either say it's too hot, it's just right, or it's too cold. And what I want to do is, given a temperature, I want to predict basically are our customers going to say it's too hot, too cold, or just right. All right, so I'm going to open this notebook here. So this is a Jupyter notebook, which we saw yesterday. So first off, I'm going to have to install a bunch of requirements to use the notebook. So I'm going to create a virtual environment, -m. And while we're doing that, so here's the raw data as a CSV. So here's the column name is response, and the other column is temperature. And so we have too cold, too hot, just right. So there's only 3 possible values here in this response column, and then temperature is just an integer. So we're assuming we've already done all of the data collection and processing and cleaning, and so now we have this more or less usable as is format. Computer is heating up here. Okay, so I've installed everything. So now I'm going to run the notebook and Jupyter notebook and then whatever file, or you can just do Jupyter notebook. That's it, and it will open up everything. Okay, so this runs a server. And just to review quickly, so Jupyter Notebook has a bunch of cells that you can execute one at a time. So this is great for iterative development. If you want to execute some stuff, try it out. Oh, it didn't work. Let me rewrite that and then execute it again. Okay, that's the result I want. Now I can move on to the next chunk. All right, so I'm gonna execute this. The first time you run it, some of these libraries will take a second to load. So we'll let that go. I think we've already kind of covered this. So this is just to show what the data looks like. So it's just going to be a list of, some customer thing, some customer complaint, and then a temperature reading. And I generated this data randomly. So here's the basically functions I use to do that if you want to do that yourself. So this is all fake data. Okay, so we have this data, and can we use this data directly in a machine learning model?
Guess you have to put them on those little matrices somehow.
Yeah. Okay. Good. Yeah. So we'll have to turn some of this stuff into matrices. So the input for model is always an array of arrays. So you have to have this. It's just a structure that it requires. So you have an outer array, and then each inner array will be basically either an it'll basically be like a record. Can we use this? Can we use the values in the response column?
It'd probably be easier to set them to like some kind of integer for the processing, maybe.
Yeah. So what we have to do is we have to give the model an array of arrays of numbers, floats or integers or whatever. But here we have text. So we can't directly use this text. We have to transform it into a number. So there's a few different ways we could do that. Can anyone think of any ways we could transform the response column into numbers?
As far as the numbers, I would do like maybe too cold to -1, just writes 0 and too hot's 1.
Okay.
And then
yeah, definitely. So I think that's very sensible. You just pick one, and in fact, I mean, you chose -1 as being too cold, right? Because negative temperatures are colder than hotter temperatures, but the machine learning model actually doesn't care. Like, it's not really meaningful to a machine learning. You just need to choose some value, and then as long as you can associate that value with the response, then that's fine. So you could swap those out, and it would be exactly the same to the machine learning model. We could also like do some wacky thing, like add up all the ASCII, the character code values of each character, and then do that. But at the end of the day, we basically have 3 different things, so we can just arbitrarily assign a number to each one of those. So I'm doing that here, just 1, 2, 3. But yeah, you could have used -1, 0, 1, or 0.82, 1,000, and 50, or whatever you want to do. Okay. And then what we're doing here in this function is we're basically just converting this text into the appropriate number. So we're just doing a check. If it's too hot, then we're going to make it 1, and then whatever the integer value. Recall that this is CSV data, so this is all just going to be text. So we need to convert that text into a number. So we'll cast it to an int. Okay, so that's all we're doing there. And now our basically final data in its usable form is right here. So we have 357. So this means it was too cold, I guess. Did I use 350? Yeah. So too cold, 57. Too cold, 55. Just right, 67. Too hot, 84. So if you're just looking at this data, it's like you know, you have to go through this process, right? This is not how, this is not a familiar, intuitive thing, but that's how it has to be. All right, and then once we have all of our data and it's ready to go form, we need to create a test train split. And the typical ratio is 80-20. So of all the data that you have, you'll kind of set aside 20% of it to use for testing the accuracy of the model. So we'll, you know, all of this stuff is just kind of complicated logic. There's actually built in, if you use scikit-learn or really any other machine learning library, there will be built-in functions that do this for you. But here I'm just doing it by hand so you can see what's happening. So we're just shuffling the samples, and then we're going to say that, you know, basically 80% of them. So here's the training samples. We're going to take 80%. The test samples will take the remaining 20%. And that's it. So we're just taking all of our data, shuffling it up, and then dividing it into an 80% chunk and a 20% chunk. And then here I talked about this, but X and Y, this is machine learning convention. So X is the observation, and then Y is basically the prediction. So you can see what all these are now. You can see the length of these. You can also look if we want to. Yeah, actually, this next one will do that. So we'll do this. So the train X, here's an observation, which is the temperature, and I want to predict, you know, does the customer, you know, is it too hot, too cold, or whatever. So here's a temperature observation and the corresponding result that I want to predict. And here's another one. This is from the test set, and then here's the result that I would predict. So I think this kind of stuff is probably the most confusing part of machine learning. Okay. All right, so once we have all of our data, we're basically like, the hard part is done. So the easy part is we're just gonna basically pick a model, and here's this one. There's a whole bunch. You can kind of just play around. This is a classification problem. You can look at all these and just try different stuff out. So you want to try stochastic gradient descent classifier. I don't really know what that is, but you can try it out and see if it works well with your data set. And the API is always the same. You create an instance of the model, and then you call fit, and you pass it the observations and the predictions. So the API is always consistent. So that's one nice thing about using a library like scikit-learn, is that once you have your data correctly formatted, it's easy to, you know, use whatever model you want. So here's the input data, which is an array of arrays of numbers. So this is meaningless, but here's like a given observation, and then the Y's. So this first thing will correspond to 0. So if we get 0, 0, we predict 0. If we get 1, 1, we predict 1. And then you just create an instance of whatever model you want, and you call fit, passing it the observations and the predictions, and then you can use it. You call predict, and then you give it some additional observation, and in this case, it predicted 1. So same thing here. We'll use the decision tree classifier, but you can use any number of other ones. So this is the reason I'm doing this one is, one, it's kind of conceptually intuitive. It's basically just a bunch of if statements, and you can actually visualize that. So you can see what the model is doing, which is not typical. Okay, so let's just take a look at the training data. So we have a bunch of temperature observations and then the corresponding customer responses. So it's, I guess, too cold, too hot, etc. Okay, so now we're just going to follow the API. We're going to create an instance and then we're going to call fit on it. And there we go. In this case, it took, this is a very simple model. We don't have that much data, but it could take a few seconds or a few minutes or hours or days, depending on what you're doing. All right. Another nice thing about this stuff is you can basically get a sense after you've trained it for how accurate it is. So this is why we set aside the test data here. So we have test X and test Y. So we've trained it on the 80% of the data, and now we're gonna just do a basically sanity check on the 20% that it hasn't seen. So this is important because machine learning models, they can be overfitted. So overfitted means it learns the nooks and crannies of the particular data that you gave it too well. So you don't want it to be too good or to be too like, you basically want it to generalize well. So if I give it similar data that it hasn't seen before, is it still going to perform well? Or did it just exactly learn every single detail about this data set? So that's what you want to, that's a problem you want to avoid. So you can do something like this. We pass it novel data and we see how accurate it is. 91%. So that's pretty good. If you're getting 100%, you should be skeptical unless your problem is very, very simple. But yeah, so at this point, we would say, okay, is this good? We could go back. We could try adding more features. We could play around with stuff. We could try different models, etc. But let's say we're happy with this now. So now I'm going to give it an input that it hasn't seen. So if you look at the data, there's no 105 temperature. So this is totally novel data that the model hasn't seen. And what is it going to predict? It predicts too hot. Okay, so obviously models are statistical models, so it's not always going to be right. In this case, it was, and we can actually visualize what the model did. So this is just representing a bunch of if statements. So that's pretty much it. So you can see that, like, if the temperature was, more than this, you go here. If it's less than this, you go here, and then further subdivisions. So you could write this out in code, but it would be pretty ugly and hard to maintain. Right? You can imagine all these nested if statements. And this is a very, very simple model. All right. Any questions? Okay, so this is another quick walkthrough. So what I'll do now is I have, just for the sake of time, I pre-deployed an example application. Let me grab the IP address. Post this in Slack. And I'll go there as well. All right, so so this is I'll walk you through very briefly the backend code, but first we'll just use it so you can see it working. So what this is you'll basically draw either an X or an O, and we'll train it with data. Everyone will draw X's and O's and submit that, and then we'll train the model on that data, and then we can test it out. We can draw a new X and see if it predicts predicts the value correctly. So the UI is terrible. I apologize, but it's just meant to be to illustrate this. So we have 3 endpoints basically. So we can train the model. So you would draw an X or an O and then click the corresponding thing. So I'll draw an X and I'm going to say that was an X. I can draw an O, say that was an O, right? So I would do a bunch of these to supply training data, and then I could go here and I just made this a protected endpoint. So you log in and then you can update the model. So it'll retrain the model on the most recent data. And then you can go here and test it out. So if I try to draw this, it should say, yeah, the model hasn't been trained yet. So everyone, if you could do just like a few observations, so just draw a few X's and O's, and then we'll see what we get. All right, cool. So I'm gonna assume that everyone's done a few. So now what I'm gonna do is I'm gonna update the model. This is just okay. So I'm gonna update the model, and this gives me the accuracy score, for the new model. So now I can test it out, and we'll see how it does. Probably drew an X. Let's see if we'll give it some outliers. Okay. So now we can do some more. So it's pretty good. Even this is a simple problem. Even with limited data, it still does pretty well. So I'm going to give it a couple more. You guys can give it a couple more as well. Okay. And then I'll update the model with the most recent data. Okay, the accuracy score went up, and we can test it out. Draw an X and an O, so that didn't get that one. Okay, it's not picking up these O's, so. It's possible that someone's sabotaging this, which is fine. But yeah, also this is just quirky stuff, and there's limited. So with fewer samples, it did better. Now it's performing worse, but it's basically guessing X every single time. So you could go iterate over this, train it some more, and then do that process. But anyway, so this is an example of something that you could do, and I'll show you the code real quick. Where is that? Oh yeah, let me show you in the front end the data that I'm getting. So I'm using a React library for this little draw thing. And okay, let me clear this. And if I draw an O, for example, I'm console logging this, but here's the raw data that I'm getting. It's basically just a bunch of coordinates. So I draw an O and it gets a bunch of XY coordinates. So each little pixel, I think, is represented by an XY coordinate. So huge, basically just a whole bunch of XY coordinates. So that's the raw data that I'm getting, and I'm sending that data in the request to my backend. And then what happens in the backend? So there are 3 views. One, so this is what we were just looking at. This is like when you are creating a new sample. So this view right here, I draw an X and I actually, yeah, right here. So I draw an X and I train it. I get this. So this train view is right here, providing a sample. So this is just normal API. I just get the data out of the request. And then I'm going to do some transformations. So I'm going to take all of those coordinates and I'm going to have to end up, what I'm actually going to do is I'm going to simplify them because, you know, I don't need all that information. It's too precise. It's more precise than I need. I could just use it directly, but in this case, I'm gonna bucket it. So I'm gonna create a matrix of 1s and 0s based on that data. So I can go here, and I'm basically gonna take that list of floats and I'm gonna round it first off. So all I'm doing is I'm just creating a list of lists where I've, you know, chopped off some of that data. And then I'm going to do the same thing here, except I'm going to simplify it even more. So I'm going to basically, it's going to have to be a number between 1 and 10. So I'm going to create a 10 by 10 matrix to represent whatever you drew. And then right here, I'm basically going to create that 10 by 10 matrix and fill it with zeros. And then I'm going to basically fill it in. So it'll be like 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, whatever. So that's what that's what all this stuff is doing. The end result is going to be a 10 by 10 matrix with either a 0 or a 1 in every position. So that's the processing, and then that data will get saved. So here I'm checking if this is valid, and I'll show you the models real quick. This is a little bit unconventional. This is not like typically you wouldn't just like take user data and then retrain the model like that, but just to show you that you can. Where's the models? So here's the data. I'm actually using an array field. So you can do this in Postgres. You can save data as an array. This is not like, you know, this is not something I would recommend you use in general. And it's especially true when you're first learning about, you know, designing database models. The intuition is to keep to store like one-to-many relationships as an array, which you definitely should not do. But you can use arrays in Postgres. And then the model, I also save the model itself as a binary field. So all of the training data is stored in the database, which maybe you should not do. This is just a kind of a quirky example, but you can save the actual training data and then the model itself that gets used. And there's a timestamp field. So every time you train the model, you get an updated one. So you keep previous models. And then when you let's say, yeah, when you update the model, it's a protected endpoint, so you have to be logged in to update the model. But it's going to grab all of the training data that is stored in that table, and then it's going to do a little bit of initial processing, blah, blah, blah. You know, it doesn't really matter. And then it's going to train a new model. And we're just doing all that stuff. We have all of our sample data that we've read in from the database. We're doing the train test split here. We're going to fit the model, and then we're going to save it to the database. So all this stuff that we did in the notebook, basically, we're just putting it here. So once they've saved the model, we can return a score, and then that model is saved. So it's the current model now. And then when we actually want to test it out, to give it a novel observation, like right here, whatever that is, that's, whoops, That's this endpoint over here. And so we have to process that same, notice it should be the same function when you submit training data, because it still has to get all that initial data, which is all of the XY coordinates, has to get put in the same format as all of the other data. So we call the exact same function for this one. And then we just predict it. We call guess, which is just gonna call the train model, blah, blah, blah. So we're gonna grab the most recent train model from the database, and we're gonna use pickle, because pickle handles binary data. And we're gonna load the model and then call predict on the model. So that's it. Yeah, if you have questions about this or you want to play around with it, you can just run it locally. It follows the same pattern as everything else. So you can just execute, run compose dev. But that's it. Yeah. Thing.